As power grids evolve, they increasingly integrate renewable energy sources, face more frequent extreme weather events, and encounter growing cybersecurity threats. These challenges, along with the demand for real-time monitoring and resilience to system disturbances, highlight the critical need for a robust state estimator to maintain the security and reliability of modern power grids. Let us compare the advantages and disadvantages of weighted least squares, the WLS, and least absolute value, LAV, state estimators, the commonly used state estimators in power systems. WLS is known for its fast computation and simplicity, but it is vulnerable to bad data and bad leverage points, leading to biased voltage estimates. LAV is more robust, as it can reject bad measurements by exactly fitting error-free measurements, but it is more time-consuming and struggles with bad leverage points. These limitations illustrate the need for a more advanced approach that combines the benefits of both methods. Let us consider an example to illustrate the robustness of WLS and LAV estimators. This example is drawn from a well-known power system state estimation book. To better illustrate the performance of LAV estimator, we added white noise at a standard deviation of 0.001. The true values of x1 equals 3 and x2 equals 12. The fifth measurement is a leverage point, because A51 is 50.0, which is significantly larger than the other values. WLS, state estimator, is highly sensitive to bad measurements. Even a single bad measurement can cause large residuals and a biased estimate. This demonstrates WLS's vulnerability in the presence of bad data, highlighting the need for more robust state estimation techniques. Conversely, LAV provides a more accurate estimation by effectively managing and rejecting the normal errors. It is important to note that two measurements, Z1 and Z5, which are exactly fitted by LAV estimator, have zero residuals because they were selected by LAV to solve the system. The robustness of the LAV state estimator comes from its ability to select a subset of measurements, considered as a basis set, that effectively excludes bad data to solve the system. This method ensures a more accurate state estimate by selecting the most consistent measurements to solve the system. The advantage of this scheme effectively rejects the influence of bad measurements on the state estimation results. Given the strengths and weaknesses of both WLS and LAV estimators, we are left with an important question. Is it possible to develop a state estimator that combines the computational efficiency of WLS with the robustness of LAV? This question leads us to the introduction of SE+. SE+, or State Estimator Plus, is an advanced state estimation method specifically designed for power system applications to combine the best features of WLS and LAV estimators. Like LAV, SE Plus selects a subset of measurements to solve the system. However, SE Plus directly selects the exact fitting measurements through measurement exchange to clean the basis set, eliminating a cumbersome search process of optimization programming based on an approximation or linearization model used by LAV estimator. Furthermore, to avoid leverage points, SE Plus uses the number of abnormal residuals in the objective function, unlike LAV, which uses their magnitudes in its objective function. Here's how SE Plus works. First, it divides all measurements into two groups, the basis set and a redundant set. It then calculates the system voltages using the basis set and determines the residuals of the redundant set based on the solved voltages. Next, SE Plus refines the basis set by replacing bad measurements with error-free ones from the redundant set. Finally, when no further cleaning is possible, SE Plus calculates precise grid operating conditions using the finally cleaned basis set. The objective function of SE Plus is to minimize the number of abnormal measurement residuals. Let's dive deeper into the SE Plus approach. The SE Plus method starts by selecting a basis set of measurements. It then calculates the voltage solution using this basis set, and finally determines the residuals of the redundant set. A bad measurement in the basis set will cause biased voltage solution. Then abnormal residuals will occur in the related error-free measurements in the redundant set. SE Plus refines the basis set by replacing the bad measurements in the basis set with error-free measurements in the redundant set. This iterative process continues until the number of abnormal residuals cannot be further minimized, ensuring that the basis set is composed of the most consistent measurements, leading to an accurate voltage estimate. Let us compare WLS, LAV, and SE Plus across several key criteria. Like LAV estimator, SE Plus selects the minimum set of the most consistent measurements to solve the system. SE Plus not only achieves 100% convergence rates, but also effectively rejects both bad normal measurements and bad leverage points. Unlike WLS, which struggles with bad data, and LAV, which struggles with bad leverage points and the time-consuming solving process, SE Plus combines efficiency with high-quality, accurate solutions, making it the ideal choice for modern power systems. Leverage point is a measurement that exerts a strong influence on the state estimate, causing its residual close to zero. In state estimation, leverage points can arise, for example, when their weight is significantly larger than others. This large weight forces the residual of that measurement close to zero. Otherwise, the objective function would increase substantially. If a leverage point is a bad measurement, it can heavily bias the voltage estimate. Leverage points are common in power systems and prevent traditional state estimators from achieving accurate state estimation. Let us consider the same example. A bad leverage point can significantly distort the LAV estimate, as it often dominates the residual magnitude, forcing the LAV to select this bad leverage point to solve the system. While LAV struggles with bad leverage points, SE Plus avoids selecting the bad leverage point Z5 because doing so would result in 3 abnormal residuals. In contrast, selecting any 2 measurements other than Z5 would lead to only 1 abnormal residual. As a result, SE Plus effectively rejects the bad leverage point Z5, providing a more accurate and reliable solution. Now let's consider an example, IEEE 14 bus system, involving topology errors. We introduced 2 topology errors on the line from bus 2 to bus 5 and the line from bus 3 to bus 4, which resulted in injection measurements at buses 2, 5, 3, and 4, becoming inconsistent with the rest of the measurements. The goal is to reject these erroneous injection measurements to maintain accurate state estimation. When using WLS estimator, the largest normalized residuals were found on line flow measurements P54 and P23, both of which are error-free measurements. This misidentification highlights a significant limitation of WLS in accurately handling bad measurements caused by topology errors, as it can mistakenly flag correct data as erroneous. Next, we applied LAV estimator. While LAV is generally more robust, in this case it also identified the largest residuals on line flow measurements, P23 and P54, which are again error-free measurements. LAV estimator mistakenly selected erroneous measurements P3, P4, Q2 to enter the exact fitting subset to solve the system, causing biased voltage estimate. This demonstrates that even LAV can struggle with accurately rejecting bad measurements caused by topology errors, leading to potential misdiagnoses. Finally, we applied the SE Plus method. SE Plus identified the correct basis set, which includes 20 line flow measurements, 6 injection measurements, and a voltage measurement, while correctly rejecting the erroneous injection measurements at buses 2, 3, 4, and 5. This accurate rejection of bad data showcases SE Plus's superior ability to handle topology errors compared to traditional state estimators. The final clean basis set of SE plus is displayed in the system, which leads to an accurate voltage estimate. It shows that all measurements in the basis set are error-free measurements. In SE plus, we observe that injections at buses 4, 3, 2, and 5 in the redundant set have large residuals, indicating their errors caused by the topology errors, while all other redundant measurements have small residuals. For example, line flow measurements on line 4 to 5 have small residuals. To further illustrate the effectiveness of SE+, let's compare the voltage solutions obtained from SE+, with those from a traditional WLS-based state estimator in a real-time case. This real case, involving 3,612 buses and a measurement redundancy ratio of 2.25, was provided by a major U.S. power company. We compared the voltage residuals obtained from the WLS estimator provided by the power company with those from SE+, sorting both sets of residuals for clarity. The results show that SE+ significantly improves the quality of the voltage solution compared to WLS, reducing voltage residuals by nearly 35%. We found that all the voltage magnitude measurements provided by the power company were below 1.1 per unit. However, some of the company's voltage estimates exceeded 1.1 per unit, whereas all of SE+'s voltage estimates remained below this threshold. Additionally, the power company's voltage angle estimates included a few large angles, comparing with the results of SE+. SE Plus clearly outperformed the WLS estimator in handling reactive power measurements, yielding much smaller residuals and significantly improving state estimation accuracy. This is especially crucial in scenarios where precise voltage magnitude estimates in an alert state are vital to prevent system-wide blackouts due to voltage instability. Additionally, a local power utility company expressed hesitation in using the WLS estimator in their control room due to concerns about the accuracy of its voltage magnitude estimates. To develop a new state estimator suitable for power company use, we conducted extensive tests on SE Plus with 25 real-world cases provided by 4 major North American power companies, each with different system structures and sizes, as well as different measurement redundancy ratios. SE Plus converged to a feasible solution within 2 seconds for all these cases and reached a smaller sum of voltage measurement residuals. We conducted extensive random testing on SE Plus across different power system sizes, including a large 13,659 bus system, which is a sample testing system in MAT power package. The tests demonstrated SE Plus's ability to consistently reject bad data, including topology errors, parameter errors, and measurement value errors, with a high success rate. 3 types of bad data were tested, with topology and parameter errors introduced on key branches carrying more than 80 megawatts of real power flow. The test scenarios ranged from 10 to 500 random errors for each type, with 100 random cases tested per scenario. SE Plus consistently rejects a high percentage of bad data across these error types, ensuring that only the most reliable measurements contribute to the state estimation results. SE Plus achieved a 100% convergence rate across all testing cases, with voltage variations remaining within a narrow range, confirming the stability and reliability of SE Plus even under severe conditions. This consistency is crucial for real-time monitoring and control of power systems. An important aspect of any state estimator is its computational efficiency. SE Plus has been shown to significantly reduce CPU time compared to traditional methods, especially for large power systems. This efficiency is crucial for real-time applications where quick, accurate state estimation is needed to maintain system reliability and security. SE Plus revolutionizes the reliability of power system state estimator with guaranteed feasible solutions for all observable systems and a high success rate in rejecting bad data. It integrates seamlessly without disrupting your setup and installs in just 1 minute. Boost your return on investment and help prevent costly outages with SE Plus as your reliable offline backup. Choose SE Plus to secure your grid effortlessly. Contact us for a free demo.